Hello and welcome to another video from the Introduction to Machine Learning lecture series. This is a beginner friendly lecture series, so do not worry, these are very basics. So if you're just starting out, this video is just for you. Okay, so let's start the video. So first we'll look at linear regression, and it is one of the linear models which is used for regression problems. Okay, so linear regression or ordinary least squares is the simplest and most classic linear model for regression. Linear regression analysis is used to predict the value of a variable based on the value of another variable. The variable you want to predict is called the dependent variable, and the variable you are using to predict the other variable's value is called the independent variable. Linear regression finds the parameters w and b that minimize the mean squared error between predictions and the true regression targets y on the training set. So let us now understand mean squared error before we get into the nitty-gritties of how linear regression works. So what is mean squared error? Mean squared error measures the average of the squares of the errors. So this is like a mathematical definition. The formula is MSE equals to 1 upon n summation I equals to 1 to n yi minus y cap I bracket whole square, where n is the number of data points and yi is the observed values or the true values, and y cap I are the predicted values by our model. So MSE is used to check how close estimates or forecasts are to the actual values. So this is used as a model evaluation measure for regression models, and the lower value indicates a better fit. Now let us look at the geometric representation of linear regression model. In geometric interpretation terms, the linear regression algorithm tries to find a plane or line that best fits the data points as well as possible. So we'll look at the simplest of examples where we have a single input feature. So this is our input feature x0, okay, and this is our outcome that we are looking for. Okay, so now this w of 0, or in this case we just have one input feature, so we have one single coefficient, and this gives us the slope of this line, and this line is called as the regression line. We'll understand what this is, and these blue points are the predicted outcomes by our model. So these are predicted outcomes by our model, and this w0 or the coefficient of x0 is basically nothing but this slope. Okay, and this value of b is the intercept. So in this case, for this equation, our intercept will be b, and the difference between this is the, see, all these points are the values which are predicted by our model. So this is the true value, and this is our value predicted by our model. So this the gap that we have is the error. Okay, so this is I think you have already come across this equation in high school as the slope intercept form, where y equals to mx plus c, where c was the y intercept and m is the slope, right? So this is the slope intercept form that we got in our high school mathematics. So the next we have is RD assumptions. So the independent variables should be linearly related to the dependent variables. Then every feature in the data is normally distributed, and there should be little or no multi-collinearity in the data. So multi-collinearity occurs when the independent variables are highly correlated to one another. Okay, so these are some assumptions. There are more, but these are the important ones. And the regression line that we talked about, or the line whose points are the values which are predicted by our model, so that forms the regression line. So the line minimizes the sum of squared difference between the observed values and the predicted values. So this regression line is a line such that the errors are minimum. So now I'll open the Jupyter notebook and see how to implement the linear regression. So I've opened this Jupyter notebook, and we'll be looking at two examples. Okay, so let's start with the example 1. At first we imported our required libraries. So we have pandas as pd, numpy as np. So as is used for giving it a name like an alias. Okay, then we have matplotlib and scikit-learn, right? Then in the next cell we define this data, and we use this reshape function to sort of like, if you do not use it, we'll get an error. Let's not use it first so that you understand why we are using this function. So let's skip it without using it. Okay, so this is just defining our, oh wait, let me run the first cell, and now yeah, so so this is basically a numpy arrays where we are storing data. Okay, we have defined this data, but if you look like if you look at this data closely, that you'll see a cubic relationship between x and y. Okay, so when x is equal to 1, y is equal to 1, when x is 2, y is 8 basically. So this will be 2 cube, right? So y is equal to x cube, 2 cube. Similarly 3, 27, like that. Okay, but we do not explicitly write the rule about the relationship between x and y, because we want the machine to learn from the data. Okay, not by any rule that we like suggest. Okay, because if we are like telling the machine that this is the rule by which x and y are related, then it won't be a case of machine learning, right? So after that what we do is we import the linear regression class from the scikit-learn.linear model, and instantiate it under a variable named lr. Okay, and in the next cell we use the fit method and supply these two values x and y to train our model. Okay, so now if we run this, we will get, okay, lr is not defined. Okay, first we have to instantiate it next. But yeah, when I do this, when I run the fit method for training our model, we see an error. It says expected 2D array got 1D array instead. So they have suggested a solution: reshape your data either using array.reshape. Okay, if your data has a single feature, or array.reshape. These are the parameters or arguments if it contains a single sample. So what we'll do is we'll just as we have used it before, we'll just use the reshape function, and yeah, so -1, run it again, same. So now it's fine, and the model is trained using x and y values. Okay, now we have this test data where we create our data, and see, because we already know the relationship between x and y, we don't need to use the train test split function, which is usually used for data sets with one data set basically. So what happens is, when you use train split function, a single data set is divided into two parts, where one part of the data is used for training the model and the rest is used for testing the model. Okay, so we don't need to use the train test split function, because we already know how x and y are related, so we don't need any output labels for our test data. So we store this under the test data, our numpy array having 11, 12 and 13, and then we do the prediction, and the prediction is okay, these are very poor predictions. It says 745, 832 and 919, but 11 cube is 1331. These are the two values. Okay, these are the two values, and so as you can see that these are very, like, we have huge errors between the two expected outcome and the true values. If you plot it now, you can see that there's a huge gap between the These are the blue ones are the predicted values, and the true values are the orange ones. So as you can see, there are big gaps. Okay, and now if we try to plot the relationship between x and y, as you can see, as we expect, it should be a cubic polynomial, right? And you can see that we have a cubic polynomial. Next we use the score method, which basically gives us a statistical parameter called r square, which is the coefficient of determination, okay, of the prediction. So it is a statistical measure of fit that indicates how much variation of a dependent variable is explained by the independent variable in a regression model, right? And the best possible score is 1, and it can be negative when suppose the model is very bad or very worse. And a constant model that always predicts the expected value of y, disregarding the input features, would get a score of 0. Okay, so this score, which is nothing but the r square value, basically tells us how close our predicted values are to the true values. Okay, so we are getting very poor results here, and there is another metric that we can use to sort of see how good our model is, and this is called the mean squared error, which we have discussed. And you can see this is also a very huge value. So one of the reason of such poor performance is the non-linear relationship between the input variable and the output variable. So as you can see, it's a cubic relationship. Another reason for poor performance is because of the insufficient data supplied while training the model. Okay, so because the amount of data you feed into a model while training it eventually decides how efficient our model will be, because it has a lot of data, the model has a lot of data to train from. Okay, so it is the ability to sort of see a pattern in the data is more if you supply more data, right? So now we'll look at another example where there's a linear relationship between the input feature and the output. Okay, so I've opened the other example. So at first we imported the libraries just like the previous example. Next, in this case, we have two CSV files, one containing data for training our model, and the other one is for testing purposes, right? So at first we save this into pandas data frame, and using the head function we printed out the first 5 rows from the data set. Next, what we did here is to check if there is any null values in the x column, right? So it says that I've used is null, that is asking if there are any null values, and printing out the values if there are any. And so wait, I'll just show it to you. Okay, so this will it'll take some time. Yeah, so if you just use the values, you can see the all the values of x, okay, in the not the values, just to check if it is null or not. So that will be printed. So for example, we have 24, so it says it is not null, so we are getting a false. Similarly, 50 not null, so false. 15 not null, false, like that. So now what we can use this any to sort of just tell us if there are any null value in the entire column, right? And it says there are no null values. Now going to the other column, which is y, if we look at it, and it returns that there are null values. Okay, there are null values, and when we look at the number of null values we have is 1. It says it has 1 because we use the sum, like total. We tried to get all the values or all the records where the y was having null. So it says 1, that means we have just one record where y is having a null value. So what we do is we drop that null value, but this is very crucial because if you have a lot of null values, it might, if you completely get rid of that record, it might influence, because if you get rid of all those data, some relevant data might just go missing, and we might have a skewed result while feeding our model. Okay, so we don't want to do that. Sometimes if the number of values is more, or if it is relevant value, okay, and one of the column has a lot of null values, so we replace the null value with some, like maybe a mean, or maybe a relevant number, okay, or a relevant information which won't tamper with what the data set actually looks like. Okay, but in our case, in this case, because we have just one, it should not matter, so we just use the drop na function to get rid of the null value. And finally, it says there are no using this line of code, train data dot is null dot values dot any, we ask if there are any null values, and it says there are no more null values, so it returns as a false. Next, we same thing, we like from sklearn.linear model, we import linear regression class and then instantiate it under a variable named lr. Next, we for training the data, we define two variables, capital X and capital Y, where we save the X column values in capital X and Y column values in capital Y. Okay, and using lr.fit, we train the model. Okay, lr is not defined, 1 second. Okay, so yeah, so this is training the model. Next, we imported the test data from the test.csv file, and again we use the .head method to print out the first 5 rows from the test data set. Okay, next we did the same thing, but one more thing. Yeah, here you can see this sort values function, and this is used to like arrange the values of X and Y in ascending order. You can like sort it out in descending order as well. Okay, using this we can just ascend the arrange the values in ascending order. Next, we have a variable called y underscore pred. Okay, where we use the predict method to sort of test or to look at the values that is predicted by our model. Okay, so these are the values which are predicted by our model that we just trained. Now the slope, or which are also called weights or coefficients, are stored under this lr.coef underscore attribute. Okay, where you can get the slope values. Next, to get the intercept, we have this attribute intercept underscore, where we get the intercept value. So now when we look at the scores, which is basically a term called r square, or coefficient of determination, and that is a statistical measure in a regression model that determines the proportion of variance in the dependent variable that can be explained by the independent variable. In other words, you can say that r square shows how well the data fit in the regression model. Okay, basically the goodness of fit. Okay, so basically how close the predicted values are to the true values. Okay, and we see that the training set score is 99.9% and test score is having a 99.8%, so it's a pretty good model. Okay, 100% is the best case scenario where all our data points are correctly predicted, but in our model we can see that 99.8% of the data are correctly predicted by our model. And if we look at this plot, we can almost see that the two data are overlapping, right? So I think this is it for this video, for this linear regression video. Next, we'll look at ridge regression and lasso regression, and do a comparative study between all these three: linear regression, ridge, and lasso regression. Okay, so this is it for this video. I hope you found this video helpful, and yeah, if you found this video helpful, do give it a like, share it with your friends, and leave me in the comment section if you have any doubts that you need answering. Okay, yeah, so I'll end this video now, and I hope to see you guys very soon.